Hello everyone. We are very happy to have Nori Iizuka here with us today. And Nori will be talking about defining entanglement without tensor factoring. Okay, so please start, Nori.
Okay, thank you very much for introduction, and thank you very much for the kind invitation. And it's also a pleasure to talk to the people in TIFR, because I always want to come back to India. Maybe I do so in the near future. Okay, but anyway, so let me start. So first I want to introduce my collaborator, Dan Kabat, who actually was my PhD advisor long time ago. And then Takanori Anegawa, he is my student. And Takanori and I and Sandeep and Sunil and Oko is also now finishing up a new paper. So yes, so Takanori is here, also there. Okay, so the talk I will give is based on the two papers which I wrote last year and also early this year. Okay, so the basic is this part, and then more interesting aspect is analyzing this paper. And now we are trying to develop furthermore the aspect which we study more. Okay, if I have time, I may speak a bit about that. So the talk is about the hourglass, and just in case, and this is hourglass. Okay, but the important point is that this neck. Okay, our prescription has similarity to this shaped neck. That's why we call it the hourglass prescription. Okay. So our talk is about the entanglement entropy, how to calculate the entanglement entropy in very complicated field theory. Okay, but more or less I basically study the free theory, and due to technicality, interacting theory is more difficult. But even in the free theory, in quantum field theory, it is not that straightforward to calculate the entanglement entropy, because as you know very well, that Hilbert space does not factorize. Okay, so this is a basic reason why in the field theory it's more difficult. Now in field theory, especially in 2 dimensions, we have many proposals. Okay, for say scalar theory, but once it becomes say gauge theory, which is more complicated theory, how to calculate entanglement entropy is more complicated. Okay, now there's beautiful works by Sandeep and Sony and collaborator, which work out how to give the nice prescription, how to calculate entanglement entropy for gauge theory in generic, and especially it is powerful enough to calculate some quantity in the U1 Maxwell theory. That I will review quickly, but the goal of my talk is not to develop that aspect. We give a alternative prescription how to calculate the entanglement entropy for the gauge theory, which is different from Sandeep's work, but the result is consistent with what he did. Okay, so that's a global picture of it. Okay, by the way, there's some noise I hear, but
is it from me? Maybe?
I don't know. Now it's better, so maybe okay. But anyway, do. Some fun noise I hear. But anyway, let me go on. And if you have any question, please bother me anytime. I'm always happy to discuss about some aspect which I may not clarify. Okay, so please disturb me anytime. Okay, so let me start with the entanglement entropy. So I just start with a very basic stuff which you probably know all, but just anyway I do it just to give the motivation of our prescription. Okay, so let's consider the field theory in D+1 dimension. Okay, here D+1 is time, but we have D dimension. But I pick up one coordinate as special because I want to split the coordinate into left region, which is x negative, and right region, which is x positive. Okay, the reason why I do it is because I want to consider the entanglement entropy between left and right. Okay, so if you are left spin and right spin, how to do is very straightforward. Okay, you just calculate what is a state as a density matrix kind of the formulation, and then trace out say left degrees of freedom and obtain the density matrix for the right only, and then evaluate its von Neumann entropy at the entanglement entropy. Okay, if left and right say spin is entangled, after tracing out left, you obtain the mixed state density matrix for the right degrees of freedom. As a result, its fundamental entropy is non-zero. So that's associated to the entanglement entropy between left and right. Okay, so that's what I say. Okay. However, this definition is very good for the case of the spin, but it's problematic for the continuum quantum field theory, as I said in the introduction. And this is simply because Hilbert space does not factorize like left and right. Okay, so this doesn't hold. Okay, but in the case of the spin, this hold, so this is good enough. There's no more issue. And this is closely related to the fact that for field theory, entanglement entropy is a UV divergent quantity, and we need certain appropriate regularization. Okay, one way to address this UV issue would be to define field theory on the lattice. Okay, for example, for spin system on the lattice, we can define entanglement entropy straightforwardly. Okay, good. And furthermore, there are more complications for the case of the gauge theory, because connection variable like links and decomposition is not gauge invariant. Okay, well, more simply saying, we have Gauss law, and that gives a global constraint on the Hilbert space. Okay, so let me give you the well-known example to illustrate what I mean. Okay, consider a sphere. Okay, field theory on a sphere, and then we split the region into left and right. Okay, now let's consider what is a Hilbert space, which is allowed. Okay, now because space is compact, Gauss law imposes total charge to be zero. Okay, so suppose you put the left region and then put several charge. Okay, is this allowed in the Hilbert space? Obviously no, because total charge is +3 in this example. So this is not allowed in gauge theory. State is not in the Hilbert space. Okay, in order to include it as a Hilbert space, we have to include somewhere -3 charge so that total charge to be zero. Okay, but this obviously implies that the Hilbert space does not factorize in such a simple case, because factorization means whatever state where suppose we can define substate, okay, in the subregion. Whatever state you have in the subregion, that you can choose independently to the state defined in the other subspace. Okay, that's a factorization. But here in Hilbert space, whenever you have +3 charge in the left region, you are forced to have the -3 charge on the right region. So left state and right space, even if you can define it, are not independent. Okay, are not independently included in the Hilbert space. Okay, so obviously this causes a problem because in previous definition of the entanglement entropy, we implicitly assume that Hilbert space factorize. But in gauge theory, even physically, we don't have such a nature at all. Okay. Okay. Now this you can say that if you have plus charge and minus charge, there's a flux line that's connect plus to minus. Okay. Now this object is non-local, connecting between left and right region, and this bothers us. Okay. This is the origin of the non-factorization in the gauge theory. This is the simplest and easiest example to understand. All right. So first, let me review what the beautiful work which Sandeep and the collaborator did. So there are several ways to avoid this difficulty and then obtain the correct answer. Okay. I will not do the same prescription as I say in the introduction. I will give the alternative way to calculate the entanglement entropy. But nevertheless, I just quickly review the main punchline of the other prescription. That's so-called the extended Hilbert space prescription. The reason is simply because they obtain the nice physical entanglement quantity in this prescription. The reason why I show this is because I want to reproduce this result in my alternative way. Okay, to see the consistent between these extended Hilbert space prescription and also our hourglass prescription. Okay, so just to motivate, there is a nice way which I will briefly introduce, and then later I just reproduce the same result, essentially reproduce the same result in our hourglass prescription. Okay, so that's why I introduce. So what is the extended Hilbert space prescription, which Sandeep and the company did? Okay, it's simple. Okay, as I say in the introduction, if you have a compact space, Hilbert space manifestly do not factorize. Okay, but in the definition of the entanglement entropy, you assume that Hilbert space factorize. So naive way to proceed is that you extend your Hilbert space in such a way that the Hilbert space factorize. Okay, meaning that you include some non-physical state. You include some non-physical state in your definition of your extended Hilbert space in such a way that the final extended Hilbert space does factorize. Okay, then you can calculate the entanglement entropy because you define your extended Hilbert space in such a way that they factorize. However, there's a catch because you extend your Hilbert space to include non-physical state. If you naively calculate the entanglement entropy in the usual method, you obtain junk, let me say in that way. Junk in the sense that that is not related to the genuine entanglement entropy. Okay, that is not related to the entanglement between left and right. You obtain something else. Okay, so the nice work which the many people did, including Sandeep, is that how to subtract. Okay, how to subtract this additional contribution, which is there because you expand your definition of the Hilbert space. How to subtract the additional contribution to obtain the physical genuine entanglement entropy. That is beautifully worked out by many people, including Sandeep. Okay, then they obtain what is a light entanglement entropy. Okay, so I will not give the too much detail of the prescription because Sandeep is here. And then, but I just quickly illustrate my intuitive understand. That's probably hopefully the intuitive as you to you. But anyway, what I want to say is that you first extended your Hilbert space in such a way that they do factorize. Okay. So in the previous example where you have compact space and you split left and right. Okay. You include Hilbert space such a state. Okay. Where you have left total 3 charge, but right 0 charge. Okay, obviously this is not physical state, but you include so that Hilbert space factorize between left and right. Okay, and then you calculate the entanglement entropy. But since your Hilbert space obtain non-physical state, the final result of the entanglement entropy contain genuine entanglement entropy. Genuine, I mean that it corresponds to the number of Bell pair after so-called distillation technique. Okay, after the distillation. The genuine entanglement entropy corresponds to the Bell pair after the distillation, but you obtain something else. Okay, something else is not related to the Bell pair at all. Okay, and one is Shannon for the sector, and the other is non-abelian color contribution, which I just briefly explain why you obtain such a thing generically, intuitively, in the simplest example. But anyway, this is a prescription, beautifully done, and then the once you know the which correspond to which quantity, once you calculate the entanglement entropy in the extended Hilbert space definition, you can extract the genuine entanglement entropy, Bell pair amount. You can calculate. Okay, that's the point. You have to subtract this non-Bell pair related quantity. Okay, that's the point. So what is this quantity? Okay, this is not related to my talk, but I just briefly explain. So first, Shannon contribution. What is this? Okay. So let me explain in the very weird example, which is actually simplest example and most intuitive to me. Okay. Sandeep, now tell me if I say something wrong.
Please.
Okay. Okay. So the simplest example I can explain to you is that consider one spatial dimension. Okay, one spatial dimension. So you have one spatial dimension, and then consider Maxwell theory, but the gauge group is not U1, but Z2. Okay, so you have only +1 and -1 of the flux. Okay, in one dimension, and furthermore, I consider pure Maxwell theory. Okay, now let's consider pure Max theory because there is no sourced object in your dynamics because it's purely Maxwell theory and no electron at all, you have only flux. Okay, simple as that. So gauge group is Z2, meaning that if you have, say, plus flux in here, due to Gauss law, you have to be plus in here. Okay. If you have minus flux in here, it should be minus as well due to the Gauss law. Okay, that's a Hilbert space. There is no plus and minus in this Hilbert space. Okay, obviously, because of the Maxwell theory, Z2, nothing is charged. Okay, so it's fine. Now let's consider the superposition of this plus plus state and minus minus state as this. Okay. Now you may say, well, this looks like entangled state. Okay, this looks like entangled state. So if you naively consider extended Hilbert space definition, assuming that you extended your Hilbert space in such a way that in left you have plus, but in right you can have both plus and minus. Okay, that's not physical, but you extend. If you calculate the entanglement entropy in the usual way, this is the same as spin system, and then you obtain log 2, obviously. Okay, but the claim is that this is not entanglement entropy in this system. Why? Well, physically, the system is plus plus or minus minus due to the Gauss law. Now we have the superposition of the plus flux case or minus flux case, and that's superposition. Okay. This is the same as superselection sector of plus flux is here or minus flux in here, but we just equally distribute it. Okay. So these two states is in the different selection sector, superselection sector. Therefore, this cannot be interpreted as an entanglement entropy. It's simply two-way of the superselection sector distribution. Okay. Mathematically, this looks like normal entangled spin, but in our Hilbert space, we cannot interpret as an entanglement entropy. Once you find this flux is plus, it simply says that due to Gauss law, this must be plus. That's it, no more than that. And you have two choices, plus flux or minus flux. So this log 2 is not entanglement, but rather it's a Shannon contribution of the flux distribution of the two superselection sector, plus and minus. So G's you have to subtract because this is not genuine entanglement entropy associated to the Bell pair. Okay, that's this part. Okay. And what about this one? You can do the similar way. Suppose you consider non-Abeli gauge theory. Okay, then you obtain quark and anti-quark. SU2 gauge group, quark and anti-quark. And then you put in the left region quark and right region anti-quark, but they must form the color singlet. Okay, so up and down for the SU2 fundamental representation, and up bar and down bar for the anti-fundamental representation, they must form the color singlet, and that is this state. Okay, but now you may say, well, this again looks like usual entangled spin, but this is not. This simply means that once you know the color of one quark, the other part of the color of the anti-quark is specified from the color singlet condition. Okay, no more than that. So this is rather obtain log 2 contribution, but this is not again related to the entanglement entropy. It just came from the Gauss law constraint for the non-abelian color group. Okay, that's also you have to subtract. So these two contributions are irrelevant contribution for the Bell pair. If you naively extended your Hilbert space so that it factorizes, you obtain these contributions as well, but they are not genuine entanglement entropy associated to the Bell pair, so you have to distinguish. Okay, so that's a prescription.
So Nori, one question. I see how the first two contributions are different, but is there a, I mean, what makes it non-physical?
What makes it?
What makes them, these contributions non-physical?
Oh, okay. In this case, okay, so the Shannon contribution, in this case, so I think Sandeep knows better than me, but let me explain. In this case, due to the Gauss law, you don't have the plus minus state at all. Is that right?
Yeah.
So in order to obtain log 2, you assume your Hilbert space contains plus plus, minus minus, and plus minus and minus plus. Then this is the entangled spin pair, and then you obtain log 2. But in our Hilbert space, we don't have such a plus minus state. Okay, so that gives a difference.
Right. I mean, a theory could be very complicated. I mean, the way you I understand this characterization in this example, but if it's a complicated theory, then there may not be a straightforward, a way of just discarding this stuff from the kind of logic that you are using, right? So,
So this is
this thing about distillation was the thing that characterizes the physical one. So maybe what I'm asking is that in what sense this kind of entanglement cannot be distilled, I guess.
Right. Okay. So the way I consider for the distillation is that you act on the one state, say in the left, and then you whatever unitary operator you are allowed to do, act on only one side, and then you are allowed only this so-called LOCC. What is that?
Local operators and
operations
and classical communication.
Yes, classical communication. And then try to make it as much as possible to the Bell pair, and then ask how much you can do it. That's what I mean by distillation. So in this simple example, I mean, you can make sure that this you cannot make it Bell pair.
I see.
But intuitively, you know what I mean, right? This plus minus is not allowed. So that's very different from, but mathematically, this formula looks like entangled spin.
Okay. Thank
you.
you.
If you extend it, you may think, oh, this is entangled, but it's not. So you have to distinguish which is physical Bell pair and which is not. That's the only thing I have to say.
So in topological theories, all this entanglement is of this type. All this just unphysical type.
That's a good.
Like Chern-Simons or 2D Young-Mills and things like that.
Naively, I would say so, but is that yes? Completely?
Yes, I think so. I think so. If you permit, Nori, thank you for this beautiful, but just permit me one comment along the lines of what you were discussing with Abhijit, which is, Abhijit, in this distillation protocol, of course, the local operations have to be physical, right? That is to say, they must involve gauge invariant operators acting on one or the other side, right? And because they involve gauge invariant operators, they cannot change the flux coming into the system because that pertains to outside, etc. Right? And that's why this part of the entanglement cannot be changed. It need not be an equal superposition in Nori's example, 1/√2, but whatever it is, it can't be changed by local operations, right? So that's why this part of the entanglement entropy cannot be distilled out by such local operations. Okay, that's right. No, Nori, what do you think?
I think so. Yeah.
And then in the cases like Chern-Simons theory, or if you take an even simpler example related to what Nori is showing here, which is a Z2 gauge theory in 2 dimensions, which is the famous Storic code, which has no low-lying excitation. So it's a topological theory, basically. You can show very explicitly that the whole entanglement you get is of this type. And the physical reason for that is that topological theories don't have any local degrees of freedom anyway, right? Local excitation. So you can't expect physically to be able to extract through local operations anything out of them, So that, but mathematically also one can.
I see.
That. Yeah.
Is there a significance to this quantity at all?
Yes, I don't know, Nori, you should say, but I just say one more thing, then I stop, which is, so, for example, the topological entanglement entropy in 2+1 dimensions that was discussed, it's which is for topological theories, that's actually of this type. But although it's not distillable, it is very useful in characterizing phases of such kind, So it's
that's actually
right.
That's actually what I try to say. So there's some quantity which is UV independent contribution, and then that you usually use to distinguish the state of your theory. Is that right? In 2+1 dimension. So the connection with that quantity.
Can I ask a question? Can I ask a question?
Yeah, go ahead.
Yeah. So how one can decide what additional degrees of freedom should be added to extend the Hilbert space from physical space to extended physical Hilbert space? So what are the criteria to add some additional degrees of freedom? in the physical Hilbert space.
Oh, okay. Sandeep may say that, but in the extended Hilbert space, because you have to allow plus and minus state, you have to implicitly allow boundary degrees of freedom, okay, so that this state is allowed. That's you implicitly do it. So in the boundary or in the entangling surface, you basically introduce additional degrees of freedom, which is beyond the original theory, so that in the Hilbert space does factorize. But anyway, the goal is that in extended Hilbert space, you introduce whatever you want in such a way that Hilbert space does factorize, then mathematically you can calculate. That's the original motivation, which as I understand, you may correct me.
Okay, thank you.
Yeah, so let me go back to the question which we are now discussing. So in the 2+1 dimension, this topological entanglement entropy quantity which people use to distinguish the state, I don't fully understand how this is related to G's argument or Bell pair, but maybe Sandeep know it more than me. I don't know. This is Bell pair issue, but that's a bit different to distinguish the state.
Yeah. No, you should go on, but I'm just saying, if you take some very simple example, just to make it clear, like the Z2 gauge theory of the toric code in 2 dimensions, then one can show that the whole entanglement is of this non-distillable type. And it's exactly the Gauss law constraint which is crucial in also obtaining the topological entanglement entropy there. You know, so the whole effect is actually of this non-distillable type. And it's true, I think also, although I have proved it less thoroughly, but I think it's true also in Chern-Simons theories in general.
So are you saying this G's non-distillable quantity is related to this topological quantity which people discuss? Is that what you're saying?
Yeah. In these theories, in these topological theories, I think the whole answer is of that type.
This Preskel-Kitaev prescription, right?
Yeah, that's right. That's right. Like in discrete gauge theories on the lattice, because they are so well defined, you can prove this.
Right.
So just for the entire general class of non-abelian toric codes and so on, one can prove it. I think it's also true in the Chern-Simons case, but we have to be a little more careful in defining the entanglement there. But
so you say even G's quantity, even though they are not directly related to the Bell pair distillable quantity, but they're still useful quantity to distinguish your phase. That's what they say. Okay. That's very good. I didn't know this. Thank you.
Sorry, perhaps I don't know, irrelevant related question. Is this quantity somehow measurable in a physical system? I mean, is this just some mathematical artifact, or can one in an experiment conclude we have this entropy, this entanglement entropy, in a topological theory, for instance?
I don't know.
Yeah.
I mean this quantity, right? I don't know.
Yeah.
No, if I can say, Nori, can I just say one small thing? Please. No, I don't know, Shiraz, but what I would say is, at least, if you did local operations involving gauge invariant operators, you wouldn't be able to access them,
Right.
And then what happens in these discrete gauge theories, like the toric code is, and this often, as you know, happens in condensed matter physics, is that, of course, the topological sector arises from an underlying theory which has local degrees of freedom, right? Like in the quantum Hall effect. So if you could probe experimentally the underlying degrees of freedom, which would require much higher energy excitations, then you can actually extract this information, through these kind of protocols. But if you restrict yourself to the low energy sector, just gauge invariance prevents you from doing that. That's what we found.
But one quick comment is that
go ahead.
If you introduce boundaries, like, one way to think about this entropy in topological systems is that it sort of comes from this edge modes that you're forced to introduce the moment you break up a system into 2 parts. So, if your algebra of operators includes these edge mode operators, then presumably you can see this entropy as a physical quantity.
But at least if you didn't have any physical boundaries, Onkar, there wouldn't be any gauge invariant operators.
I agree.
Okay. But with physical boundaries, then you're right. The edge modes are actually crucially connected to this kind of the kind of physics which gives rise to this contribution. So, okay, maybe in that sense, with physical boundaries.
Right. So you say it would become measurable if you introduced boundaries. Is that right, Omkar?
Yeah, I think that's what I was thinking. Yeah.
Okay. Yeah, that's exactly correct. I mean, yeah, this entanglement is just due to exactly the degrees of freedom which become physical with the actual boundary. That's correct.
But sorry, one question. So I know that condensed matter physicists, so in particular Vikram, for example, in our department, so the kind of thing that they study is that, let's say they have this toric code, and they perturb that, and they compute the wave function. And once you compute the wave function, this topological quantity can be computed, and then it is, as you said, the characterization of the phase. So in some sense, you can. I don't know what Shiraz means by observable, but at least in this numerical, at least in this lattice model, you can compute it and actually use it to characterize the phase, whether as you are changing the coupling, you are in the same phase or not. So it seems useful in that sense.
I understand.
So would you call it measurable or not?
Well, I don't know. Like in Chern-Simon's theory, suppose you wanted to measure the entanglement entropy of one half sphere with the other. That's same as 3-sphere partition function, which is S00, which is certainly computable, right? I mean, it's the S matrix. I mean, the Wellende S matrix, so we can compute it. That's mathematically well defined. That is fine. What I wanted to know is whether there was something that you could do in an experiment in the lab to measure that S00. So that without knowing the mathematical description of the theory, could you formulate an experimental protocol that would tell you what that entanglement entropy was?
Okay.
And I think Omkar is suggesting, which sounds right to me, that if you introduce a boundary, you could do that.
Yeah.
Yeah, if you introduce a boundary, there would be physical modes, edge modes, which would at least, be very closely related to these non-physical gauge modes which are giving the entanglement. That's correct. But that's correct. I don't know if you wanted to extract exactly the non-distillable part, what you would do on the edge modes, I'll still have to think, but yeah, they're very closely related. That's correct.
I see. You're saying, so what you mean by that, Sandeep, is that you will have this whole, the full page of this, not just the non-distillable part. You will also have distillable part, and then you would have to differentiate between them. Is that what you said just now?
No. So that's what I'm saying. I mean, you have those modes as physical degrees on the boundary, but I don't know. I don't know exactly what to do to get the non-distillable part out of that. That's what I'm trying to say. Okay. I don't know that. I don't know that. Yeah.
Thanks.
Okay. Go ahead, Nori.
All right. Yeah, it's good. So, in sum up, extended Hilbert space prescription is a good prescription, and that gives a well-defined entanglement entropy. Here, what I mean is that a genuine contribution associated to the Bell pair. However, from that, one needs to some calculation to subtract and obtain physical quantity, the number of the Bell pair obtained in the entanglement distillation. Okay. In the simple example which I show, okay, it's rather easy. But in very complicated quantity, I mean, how to you calculate this contribution? This contribution is quite non-trivial generically. Okay, so that's the motivation. So in this talk, we will propose an alternative prescription, so which is a Euclidean hourglass prescription. So the good point compared with the extended Hilbert space prescription is that this prescription is manifestly gauge invariant and has a manifest state counting interpretation, even for the gauge theory. Okay, that's what I want to propose.
Sorry, Nori, just before you get to this, one quick question. Suppose you were working in the formalism of BRST quantization. Okay. For your gauge theories to introduce a large Hilbert space with ghost sectors and so on. Now, different gauges have slightly different sort of BRST Hilbert spaces with different physical sectors. Can one show that this prescription of computing the entanglement entropy from this BRST extended Hilbert space is invariant of which gauge fixing you choose?
I think so. Yes. I think so. Yes.
Okay.
You simply asking that in the path integral, our prescription is gauge invariant. Is that what you're asking?
Yeah, a gauge invariant in the sense that you have to decide on what your extended Hilbert space is, right?
No. I don't extend the Hilbert space. By the way, no. So this is a different scenario. Okay. So
okay. No, I was talking about the earlier prescription.
Oh, earlier prescription. Okay.
Yes.
Go ask to Sandeep, please.
Yeah, maybe I should.
No, but no. You should go on with your talk. But Shiraz, just if you permit me, Nori, in one sentence, what we showed was even though the earlier description was strictly speaking in A0 equal to 0 gauge, and with the imposition of Gauss's law, that it was related to then the replica trick path integral in this gauge. But that path integral was of course gauge invariant, just in the way it's set up. So then once you define it as a path integral and you show that it is gauge invariant, you can do it in any gauge. And therefore, in fact, this is the answer, what Nori wrote down, to the replica trick path integral, defined in a gauge invariant manner. And just one last thing, which is the homework assignment you had given Ronak and me, which we didn't complete, I must say, is, but then in a general gauge vis-a-vis ghosts and so on, what is the analog of the non-distillable and distillable parts? And that we didn't fully figure out because the ghosts and all are non-unitary systems. So that has not been done.
So that is a complicated and maybe not even a very well-defined question. Yes.
Yeah, I think it would be useful to do, but we couldn't complete that assignment problem. Yes, yeah. Thank you. Okay, sorry, Nori, go ahead.
No, it's okay. But I have a quick question. Are there any time cutoff?
No.
No.
You can. I mean, the organizer should say, but you can certainly go past an hour, Nori. Okay. We are flexible up to an hour and a half or something. I think. Well, organizers should say, yeah.
Yes, of course, Nori. I mean, there have been many interruptions, so it's natural that you would go. Okay. That it's usually a tradition. Yeah.
Okay, great. But wait, just give me 1 second. I just pick up water. So just give me 1 minute.
Sure. Yeah. So Shiraz, we couldn't do that part of the story. We tried pretty hard, but I kept getting confused by the nature of these ghost Hilbert spaces and so on.
Maybe the question's not very well defined.
It should be, I don't know.
Sorry, so Sandeep, what you said is that the full answer is indeed in gauge invariant, but that does not matter what gauge we pick, but the split between the distilled non-distillable is unclear.
Yeah, because what happens, like suppose I try to do it in BRST with ghosts and so on, is that the full extended Hilbert space now gets extended to include these ghost degrees of freedom also, right? And then what happens is, in that bigger extended Hilbert space, which even has non-positive norm states, etc., then you have to identify some distillable sector, And that was Shiraz's question. And actually, frankly, it was a very important thing, because often calculationally, the other gauges are easier, right? And then if you understand all this, you may be able to do it in terms of canonical quantization, not path integral in some other gauge. So we did try, but sorry, Shiraz, we couldn't quite understand it fully.
Thank you.
Yeah, that was the story. Yeah.
Okay,
go ahead.
All right, so that's extended Hilbert space prescription, and what I want to talk is a different prescription. So that's I will just motivate you. Okay, so we will illustrate where this came from. Okay, well, just formally I give you the motivation why formally we want to consider this quantity. Okay, and then just give the several examples. This is how. Okay, so I give the prescription, but before the prescription, I just give the motivation why we want to we will calculate some partition function, not on the flat space, but on the hourglass background geometry. Okay, but you may wonder why you want to do such a thing in order to calculate the entanglement on the flat space. So I just give the illustration why formally you may think that this quantity is related to the entanglement entropy. So first I give you the motivation, which is very formal argument, but you see why I'm interested in. Okay. So to see the prescription, again, let's consider the simplest example, 1 + 1 dimensional space with coordinate t and x. Okay. On the t equals 0 times slice, okay, we want to calculate the entanglement entropy, and this is totally flat space. Okay. Now, on the t equals 0 slice, the reduced density matrix rho r is written in terms of the boost generator as follows. Okay, so Lorentz boost is generated by this quantity, t0, 0, but you multiply by coordinate x, and that's a boost generator. Okay, now formally, okay, from now on, I just give the very formal argument to give you the motivation. This formally can be decomposed into right and left contribution. Okay, the reason why I say formally is because we know that we cannot decompose left and right. Okay, but this is very formal argument. So suppose we split between right and left, okay, as this. K is written as KR minus KL, okay? So this is very formal argument, okay? Now, the reason why I say K is KR minus KL is because boost is here, okay? In right, you go upward in time, but in left, you go downward, or vice versa, okay? Now, this you can understand in the Euclidean signature, which is simply the rotation. Okay, but in one go up, but in one go down. Okay, just in order to see the orientation is opposite, I just put the definition KR so that you see the minus. Okay, that's my formal argument. Okay, so in a field theory, in a quantum field theory for the ground state, the modular operator is given by this boost operator K, and that is generically well-defined quantity. Okay. Here, K is in the whole space. I formally split into right and left. So this is not precise definition, but for K itself is formally you can define it. And then in the space, whatever field theory, as you consider ground state, you can define this quantity. Okay. Here, K, you don't have any decomposition between left and right. But the reason why I say right and left formally is because, you know, if I define low R and low left, this is what usually you obtain for the entanglement entropy, assuming factorization, which is not true. Okay. So the reason why this is I hope it's clear. You have whole region, left and right, and then splitting the x equals 0. And then this quantity is starting with here, you rotate 2 pi, and then going like this. And that's a very formal argument which people issue. Okay. But this is very formal. Okay. In the argument which I will do it, I will not assume it. I just repeat the formal argument. So whenever people calculate entanglement entropy, they formally calculate this, and that's simply because you start with this, and then you rotate 2 pi, and that's you obtain the reduced density matrix formally. Okay, and the same as lower. So in terms of the KR, which I define, modular operator is this quantity. So right is +1, but left is -1. But this imparity is simply because the orientation of the time is opposite between right and left. Okay. Mm-hmm. So everything is formal argument. So this is a good quantity, but I would say this is not directly related to the quantity we want, not directly related to the entanglement entropy which we want. Okay. So what do I mean by that? So this is again formal argument, but entanglement entropy is mutual for the case of the pure state. Okay, where you handle right state and left state in the equal footing, meaning that the entanglement entropy formally treat right reduced density matrix or left reduced density matrix in the equal footing due to the mutual nature. Okay. On the other hand, the K which we define here does not. Why? Because the modular operator, as you see in the modular operator, okay, right and left is handled opposite way, I would say. Okay, modular operator is right minus left. Okay, so this is a reduced density matrix, formal reduced density matrix for the right region. This is equal footing left reduced density matrix, but modular operator written in terms of K. Right is +1, but left is -1. So non-equal footing. Okay. So in that sense, I say delta or k, which is well-defined quantity, but that's not directly related to the entanglement entropy, which we want. Okay. So now you may see the point that in order to obtain the entanglement entropy, where you treat left and right in the equal footing, okay, because they are mutual. Instead of this quantity, you want to calculate this quantity. Okay. So here, what I mean is V, instead of the minus, I define plus. Okay. Again, this is very formal argument. So instead of the X, you obtain absolute value of the X. Okay. This is very formal. But this is, if you can define it, this is good because you treat left and right in the equal footing. So once you can calculate V and its partition function, from that, you can handle left, right, reduced density matrix formally in the equal footing. So you can calculate the entanglement entropy. Okay, so this is a formal motivation. Okay, K doesn't, but V does. Therefore, through V, you want to calculate the entanglement entropy. So this is again very formal argument. So if you define V, okay, everything is formal. In the later, I just give the prescription how to regulate the quantity so that it is well defined. But here, just let me continue the formal argument. V is plus, and you have singularity by the absolute value. But once you can define V, left and right is handled in the equal footing. Okay, this is very formal and intuitive argument. You calculate the partition function, and that is this quantity. Okay, then it's straightforward. You can show that the entanglement entropy, which is right and left, or right plus left, but divided by 2, is exactly the thermal entropy correspond to this quantity. Okay. So is motivation clear so far? Instead of the K, I just do V because we want to treat left and right in the equal footing to be consistent with the mutuality of the entanglement entropy.
One question, Nori. So does this work especially for like half space cuts, or like if you had
no. This is just illustration. As a simple example, I just illustrate this left and right in the half cut. But later we show in the spherical entangling surface, this prescription works, and then you obtain the entanglement entropy, genuine entanglement entropy contribution, even for the gauge theory in 4 dimensions.
Right, but for more general subregions, the modular operator is not known to be a local operator like this, right?
Well, right. That's true. But suppose we consider that as free theory and then ground state, you can.
Oh, okay, got it. Thank you.
Okay, but this is again the formal motivation why you want to calculate V instead of the K. Okay, because of the mutuality. So is this okay so far?
And in the eternal black hole, this would be calculating H plus H rather than H minus H, right?
Exactly. Okay. So the goal is that can we make sense of this V? Okay, that's the first question. Can we make sense of the V? Okay. Why? Because V is singular library. Okay. Because we have plus instead of the minus. So instead of the well-defined quantity, which is minus, I need opposite sign. As a result, I have absolute value. So obviously there's a singular at x equals 0. But if you have a singular, you implicitly using the factorization between left and right. But that's, you don't want to do it. Okay. So the question I want to ask is that, can you make sense of the V without factorizing left and right? If you can, that's a one step. Using your well-defined V, can you calculate the thermal partition function from this V and then evaluate entropy and then check whether this is consistent with the well-known result of the literature? That's a proposal. Is this okay so far? So that's a two-step.
Sorry, Nori, can I ask?
Yes.
Yeah, you made in the previous slide, I think you made a comment about singularity at x equal to 0.
Right. In
with factorization. Yeah. Well, can you elaborate that a bit?
Well, okay. If you formally define V, okay. So far everything is a formal argument, right? I implicitly assume factorization, okay, and then here I want to handle right and left in the equal footing and so on and so on. Then instead of the minus, you have to define plus, and that end up with a singular. But singularity means that the left and right is not smoothly connected. Okay, so you something go beyond the simple smooth geometry. You introduce some singularity in the entangling surface. So that's beyond what usually naive think. Okay. So in that sense, that's different from usual Hilbert space where everything is smooth. Now, of course, in quantum field theory, you don't want to introduce such a singular. So you want to calculate a well-defined V where everything is smooth. And then ask, given this V, which you can calculate in the whole Hilbert space without assuming factorization, evaluate partition function, and then evaluate entropy, which is a physical entropy in this system, and then check whether it matches with the entanglement entropy or not. That's the question. Is this okay?
Okay, thank you. Yeah.
All right. Okay, so let me proceed. So it's a two-step. I first discuss how to define V without assuming the Hilbert space factorization, without introducing singular at all in the whole space. Once I propose how to define V, just do the calculation in several examples. Then this is a partition function, which is a physical quantity. And then this is a thermodynamical entropy of this physical quantity. And then check whether it does match with the entanglement entropy. The formal argument so far suggests it looks like entanglement entropy, but whether it really is or not, that's a question we want to ask.
So, Nori, you haven't yet told us the a priori expectation why this should quantity match with the distillable part, right?
At this moment, no. At this moment, no. At this moment, but there's a hidden motivation because this is a physical quantity, right? This is a okay. Suppose you can define V in the whole space without left and right factorization at all. Okay, this V is a physical operator, and then you calculate physical entanglement entropy. Whatever you obtain as a thermal entropy should be physical. Now, Bell pair is a physical quantity, so we do expect it is from that viewpoint. But to see whether it really works or not, we have to check.
But computing entanglement entropy from the replica trick would be equally physical, right?
Yes, that's true. That's true. But there is some difference. But there is some difference.
But I thought that matches with the full thing and not just the distillable part.
Yeah. Okay.
So that's why I don't know why this kind of thinking is a priori at least sufficient to expect that this would give us the what you want.
I completely agree with the expectation, and we will show several examples, and then after that you can ask again.
Thank you.
But I just illustrate one simple example. Let's consider the
quick question, Nori. In the eternal black hole, there's no killing vector for which this is a charge, right?
In the eternal black hole,
I mean, there's no bulk quantity killing conserved charge for which this quantity is a partition function, is there?
You mean V?
Yes.
That's right. That's true. Only in the part of the region, this is associated to the conserved quantity. But if you don't factorize, V is not associated with the conserved charge. That's true. In whole region, no, that's true.
And even on the boundary, I mean, there's no smooth killing field for which generates this V, right?
Okay. Let me go ahead to show you the example, which probably help to illustrate before we go to the detail. Okay, maybe I said something wrong, but so I will not go to. Okay, but is this okay? The motivation why we want to calculate V? Okay. So let me go ahead. Okay, so V is associated to formally. This is only formally. Okay, that's related to the entanglement entropy where you handle left and right reduced density matrix in the equal footing. Okay, so that's we want to calculate. All right. So this partition function is very formal, and then now there's an interpretation. What is this V? Okay. This partition function can be thought of as putting a field theory instead of the flat space which you started with. Instead of the flat space, you put this on the two Euclidean cone with angle beta joint at the tip. Okay, that's the interpretation. Why is that? Because you interpret this, okay, coming from the RDR. something like that. Okay, as a tip. Okay, as a RDR, R equals 0, this is singular, that's correspond to X equals 0, that's the entangling surface. Okay, but as you increase R, it's increase, right? And then we have beta. So pictorially, okay, the formal V can be interpreted as a following. Okay, so we put the field theory on two cone. Okay, one is beta and the other is beta, but with the same direction for the case of the V. But for the case of the K, okay, as I said, one goes to this direction, but the other goes this direction, but it simply become this, you know what I mean. I show you. This is what I mean. This is what K. Okay. In one direction, it goes circle, but in the other opposite endpoint, it go opposite way. That's what K is. Okay. But since we do the V, okay, they both go the same direction. Okay. So that's the difference between K and V. Okay. And that's a cone geometry. Okay. Now in this geometry, okay, we have manifest symmetry. That's this T. Okay. That's isometry.
At a beta equal to 2 pi, what becomes of this geometry? It becomes flat.
Beta equal to 2 pi, yes, locally flat one. This becomes, there's no cone, deficit angle becomes 0, and that's attached to each other.
So the cones open up and just stack
if
up.
Beta
right?
is not 2 pi, if beta is not 2 pi, then there's a cone. Yes.
Okay.
Okay. But
Thanks.
in order to calculate the entanglement entropy, you want to introduce beta to obtain the beta dependence.
Yeah. Okay. Got it. Thanks.
Okay. So that's a picture. Now there's isometry, which is this theta direction. Okay, in this formal argument. Okay. So then we want to calculate the summary entropy. The reason why half is because this whole space contribution contains both left and right. But if you are interested in only right quantity, you have to divide by 2. That's it. Okay. So that's a formal argument for the V operator, which is a generator of the time evolution along this, I would say, set angle. In R and set angle. Okay. But both left and right, you go the same direction. In the cone geometry, where left and right is attached to each other, okay, it's isometry. Now, usual, I would say, usual prescription is that you don't have this. You have only this, but this chip you regulate. And then because of that, if you have a curvature coupling, this chip, which has a conical deficit, pick up some curvature contribution, and that yields something extra. Okay. But compared with that, we formally attach each other. And as you expect, what we'll do is that we'll regulate this region and then ask, is this V well defined? And then let's try to calculate. Okay, that's a proceed. Is this okay so far? All right, so let's proceed. So this is a UV problem, and obviously you want to regulate how to do it. Okay, usually introduce some epsilon parameter, which is a UV regulator. So instead of that, this distance goes to 0, we introduce epsilon so that it's smoothed out. Okay, that's hourglass.
So in some sense, this is a choice of regulator that distinguishes your prescription.
Exactly. So you may ask, but does my calculation depend on the regulator? You may ask that. Okay. So if we calculate the final partition function with introducing some epsilon as a regulator, and then partition function, and then as a result, some entropy, you obtain some quantity, okay? And then many of the contribution does depend on how you introduce regulator, but I just focus on the particular quantity, which is log epsilon coefficient, okay? Log epsilon coefficient, usually people look at as a universal contribution, and that is regulator independent, you can show that.
No, sorry, I had something simpler than that in mind. My question. So, I mean, here you are regulating that conical singularity by joining the two cones in an hourglass way. But another choice of regulator could have been just the smooth off the tip of the cone, which would give back the original, I mean, the replica trick.
That's what people usually do is
right.
Smooth by one. Yes.
So, is there a somehow way to kind of is there some words that you could say to justify this particular way of regulating the cone?
Well, I would say I cannot justify because it's a two different regulation, but one manifest difference is the topology is different. Usual one is a two disk, and our is a cylinder, so regulation is totally different because of the topology difference. So it's a bit non-trivial whether this one works or not compared with the usual one. But it turns out it works, and then it works in the interesting way. In the usual one, you obtain something weird, okay, in some situation. Weird in the sense that it's a bit counterintuitive. But in our case, okay, it works consistent with the intuition. Okay, that's I will show in the example.
Okay. No, I meant something like, you know, the Wilson line can now go through that neck from one side to the other.
Yes, you can.
Something right. Along. Okay.
Right. So that's I would say. Usually in this way, right. So in physically you have plus charge and the minus charge. There's a flux goes through, right? But if you disconnect it in this way, that's a bit inconsistent, right? Our one does allow such a flux go through. We have a neck.
So that is, I guess,
consistent with non-factorization. That's what I'm saying.
Sorry, Nori, I've got probably a very stupid question. If you look at a black hole, you look at an eternal black hole, in Lorentzian space, there are two sides to the geometry. But in Euclidean space, there's just normally one side, right? So you just get a cylinder, like a disk. So it's confusing me why in Euclidean space, you have two regions.
Right. In Euclidean space, what you usually choose is that you choose the temperature or the beta of the boundary in such a way that it becomes a Shiga, meaning the locally flat. But here, suppose you choose your beta different from what is predicted by the Hawking temperature, then there's a singular. Now I prepare two of them, and beta is not the same as the one predicted by Hawking temperature, but there's a singular, but I regulate the singular and then smoothly attach each other, and that's what I'm doing.
Okay, thank you.
Okay. And the reason is that because I want to consider the beta dependence to take derivative and so on and so forth. So we introduce generic.
Okay, thank you.
Okay. So again, the punchline is that no need to factorize into left and right because of this prescription instead of this. Okay, that's the point. So R epsilon, what is this? R epsilon is that it's like, suppose in the simplest example, which I show, is this one. You can do other regulation. As has it approach to the X in the large X, and then in the X goes to 0, you have some non-zero quantity, and that's okay. And then you calculate the, okay, I just tell you the scenario which I'm going. You calculate this quantity, introducing epsilon. Now, it depends on how you regulate the X equals 0 region. Okay, this quantity is different. Okay, but you calculate this quantity, and then from that, you calculate the thermal entropy. And then thermal entropy has area term. I should write more clearly. Area term plus log epsilon term plus order epsilon. Okay, that's vanished. Now, G's contribution does depend on the UV regulation. Depend on how you regulate G's, this is modified. But that's intuitive because 1 over epsilon square is manifestly depend on how you define your epsilon. Okay, UV dependent. But I just focus on the log epsilon part, which we do expect to be UV independent. More physically interesting quantity we can extrapolate. Okay. In fact, in later, if I have enough time, okay, I hope I can go. That in the entanglement example, in the 4-dimensional free Maxwell theory, where Sandeep calculate what is the low epsilon coefficient in the paper, we do by this prescription. Okay, for the entangling surface. Entangling surface is sphere case in 4 dimension, Maxwell theory in free limit. Okay, calculate V and Z entropy and look at the log coefficient. Okay, this one is dependent on how you regulate UV, but this one is not, and this one is exactly what Sandeep and friends obtain in his paper. That corresponds to the bell pair. That's what we show it. Okay, so this is where I'm aiming at. Is it okay or not? Okay, so let me proceed. So that's the orientation of which I'm going.
Hey, Nori, I'm sorry, I'm being very stupid, but I'm still confused about this two things. So let's say we're on a plane and your charge was just rotations around the plane.
Yes.
Rotations around the center.
Yes.
Right. So now, thought of in this way, if I'm just doing a rotation, there's no two things, right? Unless I'm doing a rotation by pi. So now you're rotating by something that's not 2 pi, I understand. So you get a conical deficit, but why do you get
yes. Sorry, I don't understand the question. So if it's a 2 pi, then it's only one side. If it's different from 2 pi, you have two sides, but that's smoothly attached.
Why do you have two sides? Why don't you just have one cone with a conical deficit?
Oh, that's okay. That's a usual prescription. But that's somehow associated with the left-right decomposition. Right? Okay. Let me go back to that's very important point. So where is the right? So let me begin. So this is left and right. Okay. If you assume that the Hilbert space factorization, you can define rho r only in here. Is that right? And then rho r is what? Rho r is just boost operator defined only in the right region, but 2 pi rotation. Okay. But this is under the assumption that the Hilbert space factorization. Okay. Now, this you can see it as, sorry for this, as a cone. Okay. As this figure shows. Okay. But it goes like this way. Okay. This is right and this is left. But as you mentioned, if you split in this way, okay, that's what you mentioned. Okay, you have only right field and left field, and then they decompose.
Sorry, if I may, just make one comment. So Shiraz, I think the usual prescription is to take trace of rho r, right? Take trace of rho r, and then with some exponent, and then it will give the right side of this geometry, which is right-sided. This only one cone on the right side. But now that is not what he is using. He's using trace. There are two traces. You see on that slide, trace of rho L to the beta times rho R to the beta. So it's basically two copies joined at the tip. So naively you would say that it's just product, but somehow the regulation kind of connects it.
But I'm trying to understand what these two copies are in Euclidean space. Are they related by rotation by pi?
Yes. Naively, informal argument is rotated by pi. Yes, that's true.
But I'm not seeing that this rotation by pi is relating these two copies. Because let's say this beta was nearly 2 pi. Then each of these cones has nearly 2 pi. But where is the fact that one is related to the other by a pi rotation? By an approximately pi rotation, right? I mean...
let's see. Okay. Okay. Maybe this is the easiest way. Shiraz. So this V formally we define. Okay. If you replace this as okay, look at this geometry. Do you agree this metric came as a square root of 0 of the dx d theta, but theta integration is simply beta, and then this is simply becomes this geometry dx square plus x square d theta square. Do you agree with this?
I suppose so. Yes. Please go.
Yes. So then this is simply what is the best way? Let's see. I think you are wondering this pi is this go left and right, but then again why this go to this? That's what you are.
That's right. I was trying to imagine that a pi rotation would take you from the left to the right. I'm not saying that.
So somehow there are two copies of the right. There is one copy of the right on the there is one copy of the left on the right side also, which is the antipodal point on the cone.
Right.
And there is a left copy on the right copy on the left side also, which is the antipodal point.
So but then this is different from slicing a Euclidean path integral. I mean, it's like doing two Euclidean path integrals.
Yeah. I think it's two.
It's two Euclidean path. Yes, that's right. Yeah.
Okay, so left and right, I'm just seeing two Euclidean path integrals, and you're connecting them. I won't call them left and right. Is that okay? Yeah. Okay, fine.
Yeah, but somehow the interesting thing is the choice of connecting them. Right. I mean, a priori, one would have dealt with it saying that these are two independent guys and just disconnect them. This is the standard thing. But somehow now the choice is that to connect it, and that way it makes it.
Yeah, it's like a Euclidean wormhole kind of thing, right? I mean,
exactly. Okay. So, okay, so this is one choice, and then we interpret it as this geometry, and then evaluate the V, and then partition function, and then sum entropy. Okay, that's possible. Okay, so you're right. This and this is two different. Okay, and then they are somehow related by wormhole-like type, which depend on how you regulate. But the final result of the partition function and the entanglement entropy, which is entanglement entropy is low coefficient, is independent on how you regulate these wormhole-like neck. That's what I want to say. Is okay? Okay, so that's what I want to show. Okay, so that's why we say about this. Okay, so let's.
Sorry, Nori, can I ask?
Yes.
Yes. So yeah, in the context of the wormhole thing, so there was an exchange of dominance. That the disconnected geometry is one.
No, we don't sum over the we don't sum over the this disconnected geometry and then connect, because we are doing the field theory. We are not doing the gravity. We are doing the quantum field theory.
Yeah.
There's a quantum field theory. So geometry is fixed. And then how you regulate the left and right, okay, assuming factorization, left and right Hilbert space, how they are connected is our choice for the regulation. But given this geometry, we just calculate the quantum field theory, but not gravity we are doing. Okay, therefore there's no disconnected, connected jump or such a thing at all, because we are doing the field theory. Is that answer your question?
Yeah, okay, got it. Okay, thanks.
All right, so the rest is we just proceed and then show the result. Okay, but anyway, because she has don't like this terminus left and right. Let me go. Right Hilbert space and left space, and they are connected, and therefore there is no factorization issue at all. Okay, because we choose in such a way that we don't have to face a factorization problem. Okay, just formally we just give the motivation why we're interested in V. But then if you regulate left and right is connected, no factorization. Our V partition function is a manifestly gauge invariant, physical one. We don't have any issue with the factorization. We just calculate and then physically and then interpret partition function as an entropy, which is state counting problem. Okay, that's what I will show. Okay, good. So I already mentioned regulation gives a UV difference, but log epsilon is universal. Okay. Okay, so just comment. Okay. Okay, let's comment on the field theory on a cone and varying with respect to the deficit channel. So what I'm saying is that, so here I have left and right, and then they are attached like wormhole. But usually what we do is that we have right, okay, and then there's deficit angle, and then we regulate. That's usual prescription. Okay, so let's comment on that. The cone prescription, that's this one, has a UV divergent, okay, but that can be regulated, okay, that's not the issue, okay. But however, the resulting entropy defining this cannot necessarily given by a state counting interpretation. That's a thing I would say, okay. I will just illustrate this in the very intuitive way in the answer, okay, in the example, which I will show. If I may not have time, so I just give the by words, okay. Let's consider 1 + 1 dimensional quantum field theory, okay, 1 + 1 dimension on a flat space, 1 + 1 dimension. But the scalar field has a curvature coupling. Scalar field has a curvature coupling to the background geometry. But now we consider quantum field theory, which has a scalar, which has a curvature coupling, but on the flat space, okay? Because the flat space has a curvature 0. So you may think that even this scalar field has a curvature coupling. Because you consider quantum field theory on a flat space, this curvature coupling doesn't matter at all. Okay. In fact, the ground state wave function of this scalar field theory is independent on the curvature coupling because we are doing quantum field theory on the flat space. Okay. Wave function is independent of the curvature coupling. Therefore, state is independent of the curvature coupling. Now you calculate the entanglement entropy of the ground state, splitting left and right, and what is the quantity? Okay. If you use this cone prescription, okay, light only, you obtain final entanglement entropy between left and right is dependent on the curvature coupling. Okay, that's what I want to show. Where this came, well, mathematically, okay, you have a curvature coupling for the scalar, okay, but if you have a tip of the cone, okay, that pick up the contribution of the curvature. Therefore, the resulting entanglement entropy is depending on the curvature coupling. Okay, but that's counterintuitive for me, at least. Okay, because you consider quantum field theory on a flat space. Ground state is independent of the curvature coupling. Therefore, entanglement should be so. But if you calculate entanglement entropy in usual cone prescription, due to the curvature coupling, ground state wave function is independent, but final result is dependent on the curvature coupling.
But presumably in a divergent way, right? That you can regulate, throw away by a counter term? Because the curvature is localized very near the tip of the cone.
Exactly. And that picks up the curvature contribution, and that result in the entanglement entropy dependent on the curvature coupling. Yes.
But in a way that presumably can be subtracted by a local counter term on the boundary of the entanglement surface.
Okay. You may say that you introduce counter term in such a way that this curvature dependence disappear. Is that what you want to say?
That's what I was thinking. Is I know very little about the subject, but I was thinking that that's what you would do.
That could be possible. That could be possible. Okay, that's I don't know what is the interpretation, but if you just do the honest calculation of this cone prescription, it's true that if you look at the log epsilon coefficient, that does depend on the curvature coupling, and that's the only thing I want to say.
Okay, thank you.
Okay, but I will just say, compare with that, if you do the hourglass prescription, which I just mentioned, two Hilbert space left and right is connected as a whole Hilbert space, and then just calculate the partition function, entanglement entropy, log epsilon coefficient is, you can show, independent on the curvature coupling, and that is intuitive because ground state is on the flat space. There is no curvature coupling dependence at all. That's all I want to say. That's I will show in the illustration, in the example.
So, Nori, one question. In the ordinary prescription, one nice thing is that as beta goes to 2 pi, which is where you have to take the derivative, you get flat space, right?
But you just get yes, yeah. Beta equal to 2 pi. On top of that, it's a flat space, but you take derivative. So
right,
you
right, sure. Right. No, but I was just talking about 2 pi, let's say.
Okay.
But it's precisely 2 pi.
Okay.
Right. Then it's flat space. Right.
Right. Yes.
But now in your prescription, if one takes beta equal to 2 pi, you get a highly curved geometry with the two flat, asymptotically flat pieces joined together by a very curved wormhole.
Right.
Some sort of, this kind of thing. So
I agree, except that if it's two-dimensional, it doesn't matter. But yes, I agree with what you said. Yes.
So does that somehow, because that quantity at beta equal to 2 pi is used for normalizing things, right? So I was wondering if you normalize it in a usual way, normalize the density matrix in a usual way, then why would this very curved geometry should somehow show up? I don't know. I mean, I don't see how.
Okay. So it's true that we have epsilon as a UV regulator, and then in the epsilon goes to zero limit is a singular limit, right? So you have and precisely speaking, epsilon goes to zero limit, then one tip of the cone, and then they are joined. You cannot distinguish at all. Only epsilon non-zero, you can distinguish between wormhole-like geometry or one with the smooth one, right? Now we calculate quantity, partition function, and entropy, and then we just look at the epsilon goes to zero limit, and then look at the log epsilon coefficient. Then you see what is the answer. That's what I want to say.
Okay.
You'll see in the illustration, in the example.
No, I don't even mean for entanglement entropy. I just mean at beta equal to 2 pi, the expectation is that one should get a flat space, which is like the normalization of the state.
Yes, that's
right. Here at beta equal to 2 pi, you still get a very singular geometry in the epsilon going to zero limit. Just at 2 pi.
It's not singular. It's not singular. It's like sphere, usual flat space, but here in the center, there's no deficit angle, but that's attached to the wormhole to the other flat space.
That's exactly. So that is a very singular thing, right? Or not? In the epsilon going to zero limit?
If beta is 2 pi, there is no singular.
Oh, it's not singular. Why is this not singular? I don't see that, because if you want to take two flat asymptotically flat pieces and you want to glue them through the middle, then I thought this would give rise to some singularity.
Wait. Suppose you have two plane, and then you remove one middle as a circle, then attach it.
Yeah.
It's 2 pi, right?
Yeah.
It's not singular, isn't it?
Why is this not singular? I mean,
there is no origin of singular, isn't it? I mean, epsilon is not zero.
I mean, as you go from one side to the other, there will be a huge singularity felt at the neck, right? Am I mistaken? I mean, I don't know about 2 dimensions, but in general, it looks like it's very singular geometry.
Are you considering epsilon goes to 0 limit or not?
Yeah. In the epsilon goes to 0. Even, I mean, for non-zero, it will be singular. I mean, it will be curved, but not singular. But in that limit, it probably become very singular.
Sorry. I think, I think if you regulate to whatever beta you choose and then connected by epsilon, geometry is totally regular. There is no singularity at all. I'll show in the example what is the geometry of the hourglass, which is totally regular geometry, and there is no singular at all.
Okay.
Otherwise, it doesn't make sense to how to calculate because it's a singular geometry.
Yeah.
Anyway, so time is running up. So let me go to the example. Okay, I think example is the best. So I show you the 2 example. Sorry, I'm taking too much time. 2 example is that one is the entangling surface is planar. Okay, that's the simplest example. Okay, especially in 2 dimension. Okay, but there's a simplest example, but some example is a bit non-trivial for the interpretation. That's I show it. And then I just directly jump into the more non-trivial situation where entangling surface is sphere case, which is again 4 dimension. We just do the calculation. I omit some of the technical detail. I just show you how to do the calculation. Average partition function. It's a free theory, so you can calculate and then obtain entropy and what is the result, which is consistent with extended Hilbert space Bell pair contribution. That's I will show it in the rest of the time. Okay. Is it okay? Okay. So the trivial example I start with is a 2D CFT. Okay. Consider CFT on a spatial interval like open string between 0 to pi, but I split the region into 0 to pi over 2 and pi over 2 to pi, left and right. Okay, Virasoro generator written like this, that you can see in the Green-Schwarz written textbook. Okay, now the modular Hamiltonian, which you can also write it down for the vacuum. Okay, again vacuum. Okay, and that's this. And that's it turns out it can be written in terms of the Virasoro L1 and L minus 1. Okay, but we want to do instead of K, we want to do the V, okay? So what's the point? At sigma equal to pi over 2, that's a connecting region between left and right, okay? Where this becomes sine, okay? Sigma minus pi over 2, near pi over 2, okay? And that's linear, so roughly this is like sigma, that's very similar to the previous example, but I want to do this for the V. You see what I mean? Okay. Near sigma equal to pi over 2. This is linear in sigma minus pi over 2. Okay, but I do absolute value to make it V. And then regulate by epsilon. Okay, so this is K, but I want to consider V, absolute value, and then regulate like this. Okay, so it's straightforward. Again, I keep saying that it depends on how you regulate it. Okay. But the final result of the log epsilon contribution is totally independent on how you regulate, as you can show it, okay, in many examples. Okay? But here I just choose the simplest regulation. Okay, so this is a V epsilon with epsilon regulation, and this you can interpret it as a background geometry is here. Okay, so sigma is 0 to pi. Okay. But here sigma 0 to pi, but sigma 0 to pi over 2 is left, pi over 2 to pi is right region, but they are smoothly connected at around sigma pi over 2 because this doesn't go to 0, okay, by the regulation. Okay. So the question to the previous example, this is completely non-singular geometry. Is this okay? This is smooth geometry. Hello? Okay, so this is the point I want to say, that this is all smooth
Sorry, in
geometry.
the epsilon going to zero limit also it's regular?
Epsilon 0 is a risk, but we regulate. We always regulate by epsilon. Epsilon is a regulator. We introduce epsilon as a non-zero. And then with this non-zero regulation, we calculate everything. And then in the end, we take epsilon goes to zero limit and then look at the log epsilon coefficient.
No, but the geometry is becoming singular in the epsilon going to zero limit, right?
That's I agree. That's I agree. That's I agree.
But in the cone, it's not. In the cone, in the epsilon going to zero limit, the geometry is becoming flat.
If
this is the distinction I was trying to emphasize.
If beta is sharply 2 pi, yes.
Yeah. In both cases, I'm going to take beta equal to 2 pi.
I think if beta is 2 pi, this is not singular, I think.
Well, this is what the question was. Yeah, I don't see that exactly, but yeah.
Okay. We always consider epsilon non-zero, so let me postpone that question.
Sure.
Okay, 4 months, because we don't want to consider singular. We always introduce epsilon as a regulator, as in do calculation, and what is the final result in the epsilon goes to zero.
Yeah.
Okay. That's the prescription. So this is a well-defined geometry with non-zero epsilon, and theta is beta. And then this has both left and right region, Hilbert space. We define V, and then just calculate. Okay, so that's a Cohen geometry. Okay, but this is a very simple example. We can change the coordinate sigma to y. Okay, some coordinate. We can make it like flat locally, essentially, because this is 2-dimensional. Okay, so originally we have this kind of configuration. But by changing the coordinate, we can make it like this. But this length become very long. Okay. So that's a geometry. And then it's a long geometry where the length goes to almost infinity as epsilon goes to 0. But it's a cylinder. We can calculate what is a partition function. Okay, whatever quantity you want, then you calculate. So calculate partition function, and this is a simple reason because in 2 dimensions in the long limit, you can use a Cardi formula. You obtain what is the entropy, okay, directly. But this L epsilon is a long distance, okay. Let's become this. But that pick up directly log epsilon coefficient, and then look at that, and that's you obtain the precise result. Okay, so it's very straightforward. Okay, what I did is that introduce epsilon, regulated geometry, calculate partition function, entropy. Here entropy is straightforward because in the Cardi limit, okay? And then look at the log epsilon coefficient, and you obtain the precise answer in this trivial example. Okay, good. So I can do more simple example, but probably you feel bored. So let me go to the non-trivial example, okay? So this is a non-trivial example, which I just mentioned briefly. Let's consider a quantum field theory in 1+1 dimension, 2 dimension, but on a flat space background. Okay, so R equals 0. Okay, flat space background, because R equals 0 on the background. Okay, then the theory ground state is independent of this GUG. That's a curvature coupling. Okay, wave function is independent of the GUG because R is 0. Therefore, entanglement entropy should be independent of the GUG. Okay, that's what you naively expect. Okay, here again, I do the same. You split between y into left and right, y negative and y positive. Okay, and then do some coordinate transformation. Okay, and then you can make it like cylinder, a long cylinder. Okay, but if you're not sure what I mean, is that you consider some. Sorry for that. Split left and right, introduce regulator. But it's a 2 dimension. You can do the conformal transformation to the long cylinder. That's what I did. Okay. Sorry for this. Okay. And then we calculate the curvature. Okay. We consider the quantum field theory on the hourglass geometry, and that's become this long cylinder type. Now we have a curvature because of this epsilon dependence. Okay. So there's a curvature contribution, and just simply calculate the quantum field theory partition function for this theory. That's it. Okay. Now this is a theory of the effective potential coming from the curvature coupling. Okay. Now we consider quantum field theory on the hourglass geometry because of the hourglass has a curvature locally. Okay. After the conformal transformation, the effect of the curvature survive, and that play as the effective potential in here. Okay, that's the effect of the curvature coupling. Okay. Now we calculate partition function and then look at the entropy. It's straightforward. And then what I can show is that let's look at this effective potential, okay, to understand the effect of the Guji. So it's straightforward. But the Guji contribution, if you look at the effective potential as a coordinate of the y is a coordinate, okay, then effective potential behave like this. Okay, so this is a region, okay, which you are compactify essentially, okay, because of the compact size, okay. But now because of the Guji, there's a bump, okay. That's the effect coming from the curvature coupling on the hourglass geometry. But what I can show you is that in the limit where this size goes to infinity, okay, and then in the limit of the epsilon goes to 0, where the size goes to infinity, you can show that in the partition function contribution, the effect influenced by the bump is negligible in the epsilon goes to 0 limit. Okay, that's intuitive because you consider very, very, very large effect, large size limit, as you have some order 1 bump. Okay, does that influence in the dominant contribution in your final partition function? Okay, naively you may say that no. Actually, you can show that the answer is in the epsilon goes to 0 limit, in the leading order, it doesn't contribute, as you can show. So you just calculate the final partition function, the size goes to large, and then, okay, evaluate partition function, entropy. After the several calculation, you obtain this is the answer, okay? So this is the entanglement entropy for the quantum field theory in 1+1 dimension on the flat space background, but where in your Lagrangian, you have a curvature coupling, okay? Your field theory has a curvature coupling parameterized by this Guji, okay? But final entanglement entropy I obtain by hourglass prescription is independent on the Guji. Again, intuitively, curvature coupling does affect your effective potential as a bump, but the effect of the bump is negligible in the epsilon goes to 0 limit, where the size becomes big. As a result of that, entanglement entropy is independent on the Guji. Entanglement entropy is low epsilon contribution is independent of the Guji. That's what you obtain.
I see.
Okay.
But it is different from if that Z coupling was 0.
Z, what is Z?
If I thought you were saying if you had the R phi square coupling, that coefficient you're calling, sorry, Z, yeah, that's Z.
Yeah.
This answer doesn't depend on Z, is it?
Exactly. That's a point.
So you would have got the same answer if that coupling wasn't there.
Exactly. That's a point.
Okay. And
go ahead.
You know, I just want to say, and that is what you would have expected, right? Because you were interested in the entanglement of originally the vacuum of the flat space theory.
Exactly. Vacuum R is 0, therefore your wave function is insensitive to the Z. Therefore, entanglement entropy of the vacuum should be insensitive to the Z, and that's what I would do. On the other hand, if you do the usual, this right and then tip of the cone prescription, the usual one, instead of the hourglass, where left, right is connected, okay? You obtain this tip and that pick up the curvature contribution. Your final straightforward calculation of the entanglement entropy does depend on the Guji, okay? So I just say, nothing wrong with this, okay? But I just simply say that as a normal prescription gives a bit counterintuitive answer. Contrary to this, hourglass gives more intuitive answer because it doesn't have this dependence at all. Okay.
Sorry, what is the right answer? Why do you say that there is nothing wrong with this? One is right, one is wrong.
There's no right answer. There's no right answer.
Well, there is some distillation that provides you what the right answer should be, right?
Oh, okay. Distillation, if you do the distillation, I would say Guji dependence should not appear. That's what I would say. Because wave function is independent of the Guji.
I see. So there is some, this is some well-known issue with this cone prescription.
I don't think this is an issue. I mean, entanglement entropy is just one quantity to characterize the amount of the, benefit. But what's the best way to say? I would say, if you're literally interested in only in the bell pair contribution associated with the distillation, maybe it is not the right one, but well, is that what people usually look at? I'm not completely sure. It's just one way to characterize the entanglement. That's true, but does that must be, or is entanglement entropy must be equal to the Bell pair always? That's I don't know whether it should be so or not. Because so in that sense, it's more intuitive.
There is no gauge theory issue here, right? So I thought
there is no gauge theory.
Conventional, right. Conventional quantum field theory.
Right. Exactly.
Okay. Yeah. So the one can take probably the factorization that the Hilbert spaces factorize and so on, right?
Right. Okay. Or also introducing the cone that pick up additional contribution and that end up with this Kuji dependence. Maybe I should finish. So I don't know whether this is problematic or not, but I just say it's different from the intuitive answer. That's
okay. Okay. Thank you.
So that's a non-trivial example one, and then I just
Nori, sorry. So I thought that the differential equation for the entanglement entropy with respect to variation in M, that you can get it's some kind of a beta function equation that you can use to see what the MDDM of the entanglement entropy is. There's some work which says that it has to be log of 1 over M epsilon. And I thought that the coefficient had to be 1 over 6. So there is but the Xi appearing there seems to make it wrong.
So right? Sorry, I don't
I'm saying this 1 over 6 log 1 upon M epsilon. This is I thought this was derived by some method of I forget now, Peschel and Cardi, and Shomik Banerjee here who has derived that. There is a possibility of a finite term, of course, but Xi log 1 upon M epsilon seems to not be that kind of a finite term. So yeah, so this
okay. So there may be some twist of the calculation, but what I'm saying is that simply just straightforwardly directly use this comp prescription. There's a tip which is a conical defect, and that's singular. Okay. Therefore, there's a curvature coupling does affect to this local dynamics. And then if you just naively calculate, you obtain Guji dependence. And I'm sure there's some twist which you can avoid this by doing something. But I just say naively you do that, then you obtain this Guji dependence. That's what I say.
Okay, thank you.
Okay, so that's example one. Let me go to the most interesting one, which is entangling the surface is sphere case. Okay, that's a recent one. And again, I do the same thing. Okay, so because I'm using so much time, I just go to quickly the prescription at least. Okay, how to do it, and then what is the final answer. Okay, so I consider 4-dimension Maxwell theory Fourier system. Okay, I skip the detail, but I consider the Maxwell theory 4-dimension Fourier. Space is 3-dimension. I consider the entangling surface to be sphere. Okay. Then I ask, what is the entanglement theory?
I can't hear you. No?
Yes, can you hear me now, Sami?
Yeah.
Okay, so I consider the entangling surface to be sphere. Okay, and then consider what is the entanglement between inside and outside of the sphere. Okay, that's what I ask. Okay. And then again the same. We consider what is a modular Hamiltonian in this system. Okay, and that's this given by this formula. R is capital R is the sphere. Okay, in 4-dimension. Okay, and then in this example, I consider the partition function on this geometry. I think it's okay. No, that's a modular Hamiltonian. Then what I'm saying, I think I want to consider the V. Okay. Then consider this quantity is putting the theory on this geometry. Okay. So again, this is the factor. That's previously we have this factor as absolute value. and that plays a role of this factor, okay? Because we want to interpret this as square root of g. Remember, before we have x absolute value, I regulated as x plus epsilon square. That's appear from the square root of g, and that's determine hourglass geometry. And then similarly, this factor determine what is hourglass geometry, and that's this factor. Okay. Again, small r goes to capital R. This factor goes to 0. Okay. Then we regulate by adding epsilon square. So it's essentially the same. Okay. Now we introduce epsilon and regulate. Okay. And then you calculate partition function. There's a technical issue. You want to do some wire transformation because Maxwell theory in 4-dimensional in flat limit is conformally invariant, at least classically. You may wonder you have quantum anomaly. But what we can show is that in order to calculate the partition function, quantum anomaly does contribute only beta proportional contribution because beta is a killing vector, beta direction is a killing vector. So whatever quantity you calculate, it's always add up to the beta times something. Okay. Therefore, that doesn't contribute to the entropy. Beta proportional contribution does contribute to the only ground state energy, but it doesn't contribute to the entropy. So quantum anomaly contribution, which gives a local term, because we have beta direction as an isometry, it doesn't contribute to the entropy. So that's we don't care. Okay. Anyway, we just do the conformal map to whatever we want. Okay. You can map. Okay. It's just to connect to each other to the smooth geometry as before. Then you can also consider another transformation where you have two ADS-like geometry, but that's attached to each other in the smooth cylinder geometry. And then you can calculate the partition function. Again, with non-zero epsilon, all the geometry after the Weyl transformation, you choose whatever you want. You can calculate, but it's all regular geometry. So V is well defined on this geometry. You can calculate the partition function as its Fourier theory. Okay, that's the point. So you calculate, given well-defined space, just evaluate the partition function, evaluate thermal entropy, and then look at the log epsilon coefficient. It's very straightforward calculation, and which you can do because it's a well-defined geometry, and then Fourier theory. Okay. So just one comment. In this prescription, there's no edge mode, obviously, because it's just smooth neck connecting between left and right. There's no edge mode living on the boundary. So you just calculate. I just quickly go to the show result. What is the final answer? Okay, final answer. This coefficient does depend on how you regulate your neck region, how you introduce epsilon. But this C, it turns out to be independent on how you regulate. Okay, but that's intuitive because log epsilon is UV insensitive contribution. Therefore, we focus on this. So for free scalar theory in 4D, where entangling surface is sphere, you obtain this result from the partition function. Okay, and for the free Maxwell theory in 4D, okay, sphere entangling surface, again you obtain this, and that's exactly what Sandeep and the company showed it in his paper, correspond to the Bell pair contribution after the distillation. Okay, but if you naively do the path integral approach, you obtain different contribution. Okay, and that's different from this contribution. Okay, so we obtain the Bell pair contribution by this method. That's a claim. If you naively do the path integral, you obtain something else. And then Sandeep has a beautiful paper where he shows that this coefficient and then path integral result, the difference came from the super selection sector contribution, Shannon contribution, that gives the difference. But anyway, the point is that hourglass prescription gives the physical contribution correspond to the Bell pair after the distillation. Okay, that's a punchline. So sorry for going over time. So just I finish all my talk. So summary. Maybe I just skip the summary, but I just stop by this page where there is a hourglass geometry. So that's it. Thank you very much.
Okay, thank you very much, Nori, for a wonderful talk. Let's all unmute in the talk. We have had many questions during the talk, but I hope if Nori doesn't mind, we can have a couple more.
Yes, this is, of course. Let me pick up.
So Nori, just to understand, is it true that if I, for example, going back to a previous question that was raised, if we use the hourglass prescription to compute, say, entanglement entropy in a topological field theory, like let's say, for example, John Simon's theory, then would you say that you would just get 0?
Yes.
Instead of the standard Kitaev-Breskov?
Yes, I think so.
I see. And the way that happens is because essentially by the hourglass prescription, you're changing the topology of the manifold you're computing your partition functions on.
Exactly.
Okay, I see.
So,
got it.
In that sense, so this is a bit, I would say it's a bit demerit of hourglass prescription. I thought that hourglass prescription is good in the sense that it just directly gives a Bell pair contribution, which is interesting. But on the other hand, as Sandeep said today, the other contribution is also interesting, which I didn't know before. And that useful to distinguish the phase of the state. Okay. Therefore, if you look at only the Bell pair contribution, hourglass gives a good way to calculate. But if you are interested in more information, okay, maybe hourglass is not that useful in that aspect. That's what I thought. Because it gives 0.
Yeah.
Thank you.
No, but yeah. No, but I think it's very interesting, right? I mean, physically, if you did the usual replica trick, you have these boundary gauge degrees of freedom, which are giving the super selection contribution. And now you've gotten rid of it, right?
Right.
As you have emphasized.
There's no boundary, right? There's obviously no boundary. There's nothing at all.
But what's interesting is that you land exactly on the distillable part, right?
Right.
In a sense, if you do both path integral calculations, you can get both the extractable or distillable and non-distillable part. So that's very.
In some sense, this is what usually people do, right? This is what usually people do. But here, somehow you split topologically between left and right. But here we don't. We obtain whole contribution of the Hilbert space. There's no issue of the factorization, whole partition function. So intuitively, the only quantity I can expect is a Bell pair contribution. Okay, this is my motivation because it's a physical quantity. And after the distillation, Bell pair quantity is a physical quantity. So naively, I do expect this is a quantity we should expect after this prescription. So that's our whole motivation.
Nori, it's very late and I'll discuss with you, but I wanted to just make one comment, if you all don't mind. You know, what we had shown afterwards also is if you compute more UV safe quantities like mutual information, etc., then because the super selection part, the non-distillable part, is so dominated by the ultraviolet, actually. As long as, say, you're taking, okay, let's compare just the entanglement entropy of two states, which only differ from each other by low energy excitation. So say the vacuum and some low energy excitation on it. Then, you know, the non-distillable part cancels out of that
exactly.
And is, I think, similarly for mutual information or something, those things might be easier to just show in your way of doing it, because anyway, you are only keeping track of the distillable part. You know.
I see.
Okay. Anyway, we can discuss later. Yeah, I don't know, but it may be.
So you say that the difference, the non-distillable part will in the end cancel out if you look at the mutual contribution.
Yeah.
So the subtle difference of the topology in the end will end up to essentially the similar result. That's what you expect.
Yeah, it seems so. It'd be nice to understand. It might be just easier in your way of doing it. Yeah, just to discuss more. Yeah. Okay. Thank you. Thank you very much.
Can I ask a question?
Yes, please.
Can you please show the slides you used to used an while transformation in between?
That's technical part. Yes. Okay. Sure. Just a moment. So, okay. So first look at the modular Hamiltonian, and then that determine what should be the hourglass geometry, and then from that you do the while transformation to obtain this geometry, and that's essentially Euclidean dojita. That's two spheres attached to each other. Then we regulate, and then another while transformation make it to ADS. Okay. Usually people consider the entanglement entropy on the ADS background, ADS cross S1 by using the heat kernel technique, and that's where you end up in G.
So finally, there's a geometry where theta has to be identified with theta plus beta, and there's just Euclidean ADS. Is it correct?
Theta plus
Theta. Here, this theta has to be identified with theta plus beta, and this is the Euclidean ADS, right?
This is a Euclidean.
The rest part.
Euclidean ADS, but Euclidean ADS is attached to each other.
Okay. Okay.
Because if you have only one side, you have one Euclidean ADS. But because we have left Euclidean ADS, right Euclidean ADS, and that's attached smoothly by the epsilon. So the final geometry is that Euclidean ADS for cross S1 for the left contribution and right contribution, but they are like one whole like smoothly attached on the cylinder in here, and that's this geometry.
Okay.
Okay, I think it's if there are no further questions, let's thank Nori again for a wonderful and very clear talk, and
Thank
very
you for
patient with all the questions.
Thank you very much. I learned a lot from the discussion today. Thank you very much. Thank you very much.
Great talk, Nori.
Thank you very much.
Bye.